Alright, so now let's have a look at the third example. So here I have a periodic function which is defined as negative t from negative 1 to 0 and t from 0 until 1, and then we have the information that f of t is equal f of t plus 2 again. For this case, my value of t, capital T, which is the period, is going to equal 2. Alright, so first we're going to sketch the function, which is going to be from interval of negative 1 and negative 3. So let's start sketching. So let me prepare the axis first. So this is going to be my axis. So it's supposed to be from negative 1 on this side, and I'm going to have 1, 2, and 3. Alright, so this is going to be t, and this is going to be my function f of t exists. And we're going to use the same trick as before. So whenever I want to find like how does it looks like, whenever I sketch the graph, I always use the coordinates. And that is going to be the case when we have t raised to the power of 1, because we know that when your variable t is raised to the power of 1, it's bound to be a linear function. Right, so now let's pick two values, so which is going to be the highest and lowest for this function, and I'm going to substitute right there, and therefore we'll get that when t is equal negative of 1, so my function of f of t is going to equal 1, and when t is equal 0, my function f of t is going to equal 0 as well. So negative 1, 1 is going to be somewhere up here, so let's say it's going to be a value of 1, and 0, 0 is going to be right at the origin, so the graph is going to be going down, and that is going to be the case over here, because from this function we know that the gradient is going to equal negative 1, so the graph is supposed to be going down, and the c value is equal 0, so that's what happened over here. My intercept value at f of t is equal 0. And then I'm going to do the same for the second function, t, which covers from 0 until 1. So when I substitute the value, I will get that when t is equal 0, my function f of t is going to equal 0 as well. And when t is equal 1, my function f of t is also going to equal 1. So 0, 0 is going to be right at the origin, 1, 1 is going to be somewhere over here. So this is how the graph looks like. Okay, so we have seen previous two examples for which like one function is at the top, one function is at the bottom, and it's being defined as being an odd function. So this is a different case for which my function is side by side. Okay, and I mean it doesn't look symmetric from my sketching. All right, however, we know that this is supposed to be an even function. All right, because they are side by side, they are the mirror image of each other, so it's going to be defined as being an even function. And remember, always do not leave your function like this. So the period value is equal to, so every 2 unit distance there is bound to be another cycle, so I'm going to have another cycle from 1 until 3. So that is how my function looks like. Okay, so now that we know that this is going to be an even function, of course there will be a slight difference when it comes to our calculation. Okay, now let's start with the calculation. Alright, so for B, first of all, it's going to be the same. We're going to calculate the value of omega. T for this case is going to equal 2. So omega is going to equal 2 pi over 2, which is going to equal pi. Remember, we have three Fourier coefficients, a0, an, and bn. Right, so now first I'm going to start my calculation with the a0. Okay, the thing is that, what is the difference between Fourier coefficient of even and odd function? So it's going to be the opposite. So remember, when we have an odd function, so what happened is that, so a0 and an is going to equal 0, and we have to calculate what is going to be the value of bn. So what happened is that when you have an even function, it will be the opposite. So you have to calculate for a0 and also an, and what happened is that your bn is going to equal 0. So why does that become 0? So let me explain to you a bit later in the calculation. Okay, but I want you to know that in terms of the calculation, it will be the opposite. So that is why, so when you have odd function, it is going to be much easier to calculate when it comes to odd function, because odd function you have to calculate only one Fourier coefficient, but for even you have to calculate for 2 Fourier coefficients. So now let's start with a0. Okay, let me put the formula for a0 first. So a0 is given by, let me put that higher, so I have enough space to calculate for a0. So a0 is going to equal 2 over t, so the integral from d until d plus t of the function f of t dt. So it's a very simple function. And again, every single time before you start substituting f of t, right, so we have to inspect the property first, but I am going to substitute whatever values that I needed first. So I'm going to have 2 over 2, my integral, and by now you should know the value of d and d plus t already. So d is going to be the highest value from the function f of t, and d plus t is going to be, is going to be the lowest value and the highest value of the function f of t. So here it's going to be from -1 to 1, so of the function f of t dt. And of course, like before, you substitute f of t, so inspect the property first. And from our sketching, we figured that f of t is going to be an even function. And of course, if it's an even function, we can always change the limit. So here, what is going to be my new limit? So my new limit is going to be half of -1 to 1. So it's going to be from 0 to 1, and I have to multiply by 2 because I want to consider the whole area. And now I'm going to substitute the function f of t. And if I have area that covers from 0 until 1, so the function that I'm going to use is going to be this one, which is going to be t. So I'm going to have t dt. So that's how it looks like. Alright, now all I have to do is start integrating. So I'm going to have a 2. So when I integrate t, that will be t squared over 2, evaluated from 0 until 1. Okay, now I'm going to start substituting. So I'm going to substitute right here. So from t equal 1, and then when t is equal 0. So do not miss out the 2 outside, so put over here. So when I substitute t equal 1, I'll end up with 1 squared over 2 minus 0 squared over 2, for which I will end up with 2 minus a half, and that is going to be 1. Okay, so that is going to be my function E naught. And I have remind you this at the beginning of this subtopic when I told you about E naught, En, and Bn. I tell you that E naught is always a constant. It's always going to be a value. Okay, it cannot be a function. It is always going to be a constant. So that is E naught. So now I'm going to proceed my calculation, but next I'm going to proceed to my En. So this is going to be the formula for En. So I'm going to have d plus t. So f of t cos of n omega t dt. So now let's start substituting. So I'm going to end up with 2 over 2. The integral is still going to be from -1 to 1 of the function f of t. So cos of n pi t dt, because we know that omega is going to be pi for this case. And from our inspection, from our sketching, we know that f of t is an even function. So cos is also even. And when you multiply two functions with the same property, even and even, so the outcome, the product is going to be even as well. So now let's simplify this because this is an even function. So I'm going to change the limit. So my new limit is going to be from 0 until 1, and I have to multiply by 2. So if I consider f of t from 0 until 1, so that is going to be the function t. So I'm going to have t, so cos of n pi t dt. So that's how it looks like, right? And again, I have mentioned this during the previous example. For the case of Fourier coefficient, it's either direct integration or integration by parts. So here, I'm going to do integration by parts. My polynomial is going to be t, and my trigonometric function is going to be cos of n pi t. And I differentiate this repeatedly until I get a 0, t1 and 0. And integrate cos, I will get sine of n pi t over n pi. And when I integrate this again, I will get negative cos of n pi t. And that is going to be over n pi square. So now draw diagonal arrows and then put plus and also minuses on the sides. Alright, so now I'm going to start substituting my integration. So the first term, I'll end up with t sine of n pi t over n pi. So that is my first term. And my second term is a negative multiplied by another negative. So that's a plus 1. So multiplied by cos of n pi t. And that will be over n pi square. And I'll evaluate this from 0 until 1. And then next, I'm going to substitute when t is equal 1 minus when t is equal 0. So where are all the t's? So here are all the t's that I'm going to substitute. Alright, so now, so this is my 2. So when I substitute right here, so t is equal 1, I'll end up with 1 sine of n pi. So it's going to be sine of n pi over n pi. So that will be the first term. So the second term is going to be plus, so cos of n pi, and that is going to be over n pi square. So this one t is equal 1. So minus when t is equal 0, I'll end up with 0 because it's 0 sine 0. And the other one, I'm going to have cos of 0. So it's going to be cos of 0 over n pi square. So this will be my substitution. Okay, so now let's simplify whatever that could be simplified. What do I mean by that? First is going to be sin n pi. We know that anything that is related to sin n pi is going to be 0. So I explained this to you before why. And when I have cos n pi, I can replace that by negative 1 to the power of n. And cos of 0, the value is going to be 1. And do not be, like I come across this so many times, for which like when cos 0, student put 0 of it. No, press your calculator for it, double confirm what is the value of cos 0 if you're not sure about it. Okay, so now when I simplify, so I'll end up with a negative 1 to the power of n over n pi square. So that will be at the bottom. So it's going to be for the first substitution t equal 1, and for the second substitution t equals 0, I'll have minus 1 over n pi square. And I'm going to factor out whatever that are the same between the both of this, and I'll end up with something like this. So I'm going to have 2 over n pi square. So I'm going to have negative 1 to the power of n minus 1. So that is going to be the outcome of my Bn. So if you notice, if you have seen the video on example number 1, so you will notice the similarity between this. So the fact that we have this term which is going to be negative 1 to the power of n. And I did tell you this before, the fact that when we have n is an even number, so negative 1 to the power of n is going to be positive of 1. So it's always going to be the power of 2, power of 4, power of 6. We know it's going to be positive of 1. And when n is odd, what happens is that my negative 1 to the power of n is going to be negative of 1. Negative 1 to the power of 1 to the power of 3 to the power of 5 is always going to be negative of 1. So that is why I can make a generalization of this. I can write that Bn. Okay, so what happened when I have when n is even? Okay, I'll then end up with something like this, 2 over n pi square. So when this is even, automatically this term right here, so it's going to be positive of 1. So 1 minus 1, so that is going to end up with a value of 0. So later I know that this is going to be 0. And it's going to be a similar idea when n is odd. So what happens is that I'm going to have 2 over n pi square. And when n is odd, I'm going to have negative 1. So this is going to be negative 1 minus 1. And this can actually be simplified too. Right, at the top, I'm going to have 0 when n is even. And I'm going to have, this is going to be negative 2. So therefore, I'll end up with a negative 4 over n pi square. So when n is going to be an odd number. So now, if you remember what we did in example number 1, so because for a case of n even, it's going to equal 0, I don't have to bother with that anymore. So I have to come up with a series concerning when n is an odd number. Right, so this is not E naught, this Bn, this is actually my En. I mistaken that. So this is actually our calculation on En, not Bn. We haven't got to Bn yet. Right, so now that we have done with the A naught and En, then only we are going to proceed our calculation with Bn. Right, so this is going to be my formula for Bn. So it's going to be 2 over t integral from d until d plus t. So f of t sine of n omega t dt. So the previous one, so it's being multiplied by cos. This is the formula. But for Bn, we multiply it by sine. So when I substitute, I'll end up with something like this, 2 over 2 integral from negative 1 to 1 of the function f of t. So sine of n pi t dt. So that's a dt right here. And when I wanted to inspect the property, like I wanted to know what happened to the product. So f of t from our sketching is even and sine is going to be an odd function. And we know when they have different property, even and odd, so this is supposed to be an odd function. So when we integrate an odd function which are symmetric from negative 1 until 1, we know that this is going to end up as being 0. So that is why in your calculation, when you come across for even function, okay, so it's going to be very similar idea for odd as well. So just state that Bn is equal 0. right? So you don't have to go through all these calculations over here, so no need. So just simply put that Bn is equal 0. Why? Because we know that this is always the case when we have an even function. Okay, so now that I have all my Fourier coefficients already, so I'm going to do next is I'm going to put together my function f of t. Right, so my function f of t according to the Fourier series formula is going to be a half a naught plus sum from n equal 1 to infinity of a n cos of n omega t plus sum from n equal 1 to infinity of bn sine of n omega t. Alright, so for this case, the only one Fourier coefficient is going to be 0, which is going to be our bn. So we have two Fourier coefficients to substitute, which is going to be a naught and also an. Okay, now let's start by substituting a naught. So from our previous calculation, we know that the a naught, the value is going to equal 1. So I'm going to substitute right here. So it's going to be half multiplied by 1. And then I'm going to have a sum for the case of n. Okay, but you have to be careful right here. But because, so this is only concerning when n is odd. So I'm going to put over here. So this is only for the case that when we have n is odd. So our an function, so that is going to equal negative 4 over n pi square. And that is my en, so I just substitute my en right there. So that will be multiplied by cos of n omega, so which is equal pi. So I'm going to have cos of n pi t. Okay, now, so we have to change this right here. So we cannot leave it in terms of n is odd. So we have to always make the series from n equal 1 until infinity. So this is what I mean. So here I'm going to have a half multiplied by 1 is going to be a half. But remember in Fourier series, so the series has always to start with n equal 1 to infinity. Remember I did mention this to you before when I explained to you about the first example. So when n is odd, what you're going to do is, so you're going to replace all the n in the series to n minus 1. And for the case that when n is even, if you ever come across any, so you're going to substitute that n is going to equal to n, because we know that anything that is a multiple of 2n, so that is going to be an even number. And anything that is in term of 2n minus 1, so that is going to come out as being odd. So therefore for this case, what happened is that, so I'm going to end up with a negative 4 over, so where are the n's? So let's highlight all the n's so we know where are we supposed to substitute. So there's going to be 2 n's in there. So I'll end up with here. So let me put a bracket around. So I'm going to have 2n minus 1 multiplied by pi square. And here I'm going to have cos of 2n. So instead of like writing the whole thing in red, let me just put whatever the i's substitute in red instead, so it's going to be clear for you. So I'll put that again. So it's going to be negative 4 over, so there goes my n. So I'm going to replace that by 2n minus 1, and then I'm going to have a pi, so close the bracket and square, and here I'm going to have multiply by cos, so there goes my n, so it's going to be 2n minus 1, and then that is supposed to be multiplied by t. So let me put a border over here so it doesn't bother with our function. And let me sort of like simplify that a little bit more just to make it a little bit neater. Okay, so this series, whatever is not related to n, so I can actually pull that in front of the series. And I'm actually concerning, and I'm talking about the negative over here. So I can bring out the negative to the front, so that is possible as well. So I'm going to write it as negative, and I'm going to bring out the 4 as well because it's not related to n, and even the pi square underneath. Okay, so in here I'm just going to leave anything that is related to n, so which is going to be, for this case, I'm going to have cos of 2n minus 1 pi t, and that is going to be over 2n minus 1 square. So that is going to be my Fourier series. That's it. Okay, remember when we have an even function, so what you have to do is you have to calculate for a naught and and bn is going to be 0. Okay, so I have shown you 3 examples so far, so 2 for odd, 1 for even function. But the thing is that this Fourier series, it comes with a lot of exercise. As long as you do a lot of exercise, you will be able to experience many type of function, and that should be super good for you. So like, because there's not going to be that much variety of the calculation that you're going to come across for Fourier series, and even the integration is not that challenging because it's always going to be integration by parts. Okay, so for next example, I'm going to show you the case